again, you know, like, probably not.
Okay.
You know, most of the stuff that I would give you, I would put in the OneNote to get you visually rather than like piling paper on top of you. I try not to make more copies than I need.
Yeah.
The thing.
I did that, yeah.
Safety forests.
Yeah, I mean, I try. You know, some stuff needs to be printed, like it was classwork. Okay, you can't do something different.
Okay.
I handle something to do, but you know, the PowerPoints and everything. I try to keep everything digital when I can, unless it's like you need to fill this out and turn it in. Then go print those handles too. But all right. So again, these the notes we're doing. I want to remind you that these PowerPoints we're looking at, they're all available on My Notre Dame to download, and you can have them to go through again. If you're watching, you notice that I pulled up the screen recorder, so this lesson that we're doing right now is being recorded. I'll post this to the My Notre Dame page under the link, so if you wanted to go back and rewatch something or listen, like he said something in here that wasn't really on the slide that I thought was important, I want to go back. I missed it, I didn't write it down, but I remember him doing it, I want to go back and find it. But this, what we're doing right now, should be pretty familiar, I think. Even the things that might be kind of new are pretty simple. So, we're basically here going to start by talking about the different types of number sets. So we'll start with the natural numbers and the integers. So the natural numbers are 0, 1, 2, 3, 4. Whole numbers only, no negatives. These little symbols, like this symbol, this funny symbol N, or for the integers, that funny symbol Z, those are important. You should recognize those. That'll happen in instructions or, you know, on assignments or in the tests. That it's a given that we're hoping that you remember what these symbols are. Now they're should not be new symbols, but if they feel new to you, you should make sure to note at least that that symbol means that. The integers contain all of the natural numbers, but also the negative whole numbers. So -3, -2, -1, 0, 1, 2, 3, all integers. And this idea that like one of these number sets is nested inside the other one is on purpose. This is super common in mathematics, that you take something, you find a procedure that works for that, and then you go, okay, can I extend the stuff that I'm using and like modify the procedure so it still worked on the old stuff but also works on this new stuff, and like slowly build and build and build out. Getting more and more general. So an example of something that's not a natural number would be -1. -1. Why is it not a natural number? Because it's not positive. What else? What's another example that's like a different kind of example?
2/3.
2/3. Why is that a problem?
Because you don't naturally count that way.
It's not a whole number, right? The natural numbers have to be whole numbers. They're just the counting numbers. Nobody counts 1, 2, 3, 7, 8. You know, like you don't do that. Great. An example of something that's not an integer. 3 is an integer, right?
4/5.
Yeah, another fraction again, right? 4/5, 2/3 still works, right? Good. Everybody feel all right about natural number integer? Should be easy, right? It's not the first time we're seeing this. Want to note that sometimes we'll talk about z plus and z minus. Z plus are positive integers. Z minus is negative integers. What's the difference between z plus and the natural numbers? 0 is the answer. 0 is a natural number. Z plus is positives only. Remember that 0 is neither positive nor negative. So the only difference between Z plus and n is the number 0. As an aside, not something you have to worry about, but I'll make mention of this. The natural numbers, depending on the context that you're looking, could include 0 or could not include 0, depending on the context. In this class, it'll always include 0. But if you're reading elsewhere, you may see the natural numbers listed as not including 0. It just depends on context. All right. Next up are the rational numbers. That's Q. We define the rational numbers as the quotient of two integers, with the one caveat that you're not dividing by 0. Right? So we usually say that Q is P over Q, where P and Q are integers and Q is not 0. So essentially, these rational numbers are anything that you can write as an integer. So for example, can write as a fraction. Excuse me. So for example, 7. Is this a fraction? No. Can you write it as a fraction? Yes, you could just make it 7 over 1. So is it a rational number? Yes. How about 1.5? Yes, right? How can you write it as a fraction? 3 over 2, or you could call it 15 over 10, right? You just take the decimal and the terminating decimal and divide it by a power of 10, right? Yes, sir.
So you can like write, like integers as rational numbers, but you can't put rational numbers as integers.
Some rational, like 4 over 2 is 2,
Yeah.
right?
Yeah.
But like 2/3 can't do anything, right? So sometimes is the answer to that. So if we think about, we've seen that some decimals we can write as rational numbers, right? We just saw that 1.5 we could write as a rational number. Are all decimals, can we write all decimals as rational numbers? No. Okay? Can I look at a decimal and tell whether I'm going to be able to write it as a rational number or not?
Yeah.
Yes. What am I looking for?
The repeating ones.
Okay, very good. So if a decimal is repeating, as like 0.3 with the bar on the top, anything that repeats we can rewrite as a rational number. Do you need to know how to do that? No. Some of them you might recognize, like 0.3 repeating. I would hope that everyone recognizes as 1/3, right? Now, if I have 0.123 repeating, I'm guessing that nobody's going to know that fraction off the top of their head. There is a way to do that. It's beyond the scope of what you need to do. You just need to recognize that as a rational because it repeats. Okay, so that's one type. If the decimal is repeating, rational number. What's the other thing that we look for? If it terminates, excellent. Like 1.5 terminates. Any terminating decimal can be written as a rational number. So those are the two things you look for on a decimal. So the things that we cannot write as a rational numbers have to be not repeating and not terminating. What kind of number does that sound like?
Square root.
Oftentimes square roots. Can you give me an example?
Like square root of 3.
Square root of 3. Very good. It's an example of a decimal that does not repeat and does not terminate. So your square roots that are not perfect squares, square roots, I should say, of natural numbers that are not perfect squares, those will be irrational. That's what we call numbers that are not rational, is irrational. Okay, that's one good class because that's a lot of them. There's two other specific numbers that you should think of when you think of irrational numbers? Pi is one of them, excellent. And the other, E is the other one, very good. Yes, pi and E are your two canonical irrational examples. And then your class of square roots are good ones. Everybody feel good on what's a rational number and what's not? Okay. The last class are the real numbers. And the real numbers are essentially anything that can be written as a decimal. So pi, e, square root 3, all real numbers, but are not rational numbers. Is there anything that's not a real number?
Get negative square root.
So yeah, something that has an I attached to it. So if you have a negative square root, that gets an I on it. If you have an pure imaginary number like 2i, if you have a complex number like 7 minus 5i, something that has an imaginary part to it, or a non-zero imaginary part, those are all things that are examples of not real numbers. So again, your small, or your innermost, like Russian doll, are the natural numbers, and then the integers go around that, and then the rational numbers go around that, and then the real numbers go around that. So they all nest inside of one another, right? Does everybody feel good? Okay. Beyond the scope of this class, but kind of interesting, if I ask you the question, which is there more of? Integers or rational numbers, or I'm sorry, integers or natural numbers, what would you say? Luco, you said integers. Why are you saying integers?
You can go negative and positive.
Okay, because the integers has stuff the natural numbers don't, right? But what if I said this? What if I said, okay, that makes sense, but if I can show you that I can take one rational number and pair it up with one integer, and I can do that for every integer value, then they have to have the same amount of stuff, right? If I have one pile of things, or I have two piles, and I can pair them up 1 to 1, for everything in the pile, I should have the same number of things, right? I can do that. Here's how I'm going to do it. Compare 0 to 0. I'm going to take the odd natural numbers, pair those to the negative integers. I'm going to take the even natural numbers and pair those with the positive integers. And that'll do it. So they have the same amount of stuff in them. Now, this idea of same amount of stuff, we don't say they're equal, but we say they have the same cardinality. That's the math word. How about integers and rational numbers? Which one do we think there's more of? You think that, right? And guess what? It's the same. Yeah, you make this. Now, the argument here is much more complicated, well beyond, like, I can't just kind of state it, kind of hand wave you like I did before. You have to make, like, this grid, and you gotta write all the possible fractions, and eliminate the reducible ones, and then you can make, like, this diagonalization, like, trace through it, like, on a diagonal, and, like, but it works. You know, this mathematician named Gregor Cantor made this argument to prove that they are actually the same. Rational numbers and real numbers. Fundamentally different sized. So even though both sets are infinite, the magnitude of the infinity for the real numbers is bigger than the magnitude of infinity for the rational numbers. It's like a different size of infinity, which is weird to think about because it's an infinity. It's not. There are different sizes of infinity. Guess what? There's infinitely many sizes. So, like, you sit on that for a minute and But that's honestly the way it works. Now, any of these things I talked about, is this important to you in terms of this class? No. When we talk about the sizes of these number sets, no. Not, it's just fun to talk about, kind of interesting. Yes, sir.
So why aren't like irrational numbers a set of numbers? Like they're just not like a.
So we don't denote them as a set with a specific symbol, mostly because it's really hard to define. Because we really are defining them as like the difference between the set of real numbers and the set of rational numbers. We can't, it's really difficult to construct them from pieces like we did. You know, we took the rational numbers and we built them out of integers. It turns out you can take the real numbers and build them out of the other piece, and it's really complicated though, so usually we don't write it down that way, but you can. But that's the idea. Is that okay? So, oops, didn't I have a picture on that? No, is it just not? That's supposed to have a picture of like. Oh, come on now. What are we doing? Okay. This is supposed to have a picture here where it has like natural numbers surrounded by integers, surrounded by natural, you know, where it just shows the number sets nested inside of one another. Sorry, I don't know why it's not coming up. It came up yesterday, which is the part that's really making me angry right now. Next up, we're going to talk a little bit about SI units. When we say SI units, what are we talking about? Yeah, the units of measurement we use for science, right? So those are SI, I think, stands for like System d'International. It's like a French term for that. I know that, right? That's fun. So examples of SI units. Do you need to know or memorize any of this stuff? No. You should recognize like meters and kilograms and seconds as ways to measure like length and weight and time, or you know, like that's all we're talking about. That's as much as you need to know. You don't need to know the specific names of some of these more obscure units. You don't need to like. This is just examples. Okay. We're not big on memorization in this class. Temperature in particular, we should remember that there are 3 commonly used temperature scales. There's Fahrenheit, Celsius, and Kelvins, right? US uses Fahrenheit, everybody else uses Celsius, and scientists use Kelvins, typically. Right? Remember that from your science class? If you had chemistry, you do a lot with Kelvins, right? Because all the gas law stuff is all needs to be in Kelvins. Down below, you see the conversions for how to convert between Kelvins and Celsius, and then Celsius and Fahrenheit, and then Fahrenheit to Celsius. Do you need to memorize these formulas? No, they would be given to you. Do you need to be able to use the formulas? Yes, you should be able to use the correct formula and plug the numbers into the correct place to get the correct output. That should be doable, right? What if I wanted to take Fahrenheit to Kelvins? What would I do there? I don't have a formula to go from Fahrenheit to Kelvin. Alex?
Wouldn't you just do like Fahrenheit to Celsius and Celsius to Kelvin?
Bingo. So just a 2-step conversion, right? Good job. Everybody feel okay? Again, no need to memorize any of these. They would be given to you. Do you need to know like the boiling points in these things? No, it just kind of like, I don't know, enrichment or whatever. For the SI units, they all have, we can all attach the prefixes to them. As far as this class is concerned, you should recognize what the prefixes for milli, centi, deci, deca, hecto, kilo mean, right? That they're just 10 times the previous one. Right? And this should be, I'm hoping, real familiar from your science classes over the years that like, okay, these are the 6 easiest ones to remember. I got these, Mr. Gulick. The thing that we do need to be a little bit careful about are some of these derived units when we want to do a unit conversion. So if I want to go from like square meters to square centimeters, or cubic meters to cubic centimeters, there we have to be a little bit careful. We'll do an example in a second. But when we talk about a derived unit, that means that it's a unit that's the product or quotient of multiple SI units. So meters squared is meters times meters, the product of two SI units. Meters per second is the quotient. Meters divided by seconds is the quotient of two SI units. You can add SI units together, doesn't make them derived, right? Meters plus meters is just still meters. Meters plus seconds makes no sense. All right, let's look at the example here. So if I just want to go from centimeters to inches, I just multiply by the conversion factor one time. I know that 1 inch is 2.54 centimeters. I set up my little conversion and I multiply through and I'm done. I'm left with 3.94 inches, right? Everybody feel good there? If it was 10 square centimeters, I have to do that conversion factor twice. Because I cancel 1 centimeter and then I cancel the second centimeter, right? Because centimeters times centimeters is what centimeters squared means. So I have to use the conversion factor twice because I have 2 times I have to cancel out the centimeter unit, right? That's the place that students make the mistake because they only do the conversion once rather than multiple times. So if this was 10 centimeters cubed, I'd have to do the conversion factor 3 times. You guys are catching on. This is almost assuredly going to be a test question in this kind of fashion, where I ask you to do a unit conversion for a derived unit like this, just to make sure you're paying attention to this day. So I'm going to say that one more time. This almost certainly is a test question. So if you're taking notes and you wanted to make note of that, that's probably a decent idea. Not that this is difficult, but like, it's easy to forget, right? Is the only reason why I'm making an emphasis, because I don't want to see you get it wrong, because it's like, oh yeah, that thing we talked about for one day I had to remember to do. It's like, this is me trying to make sure you remember. Okay, I'm going on. I see a lot of people writing. Are you writing down the examples, or are we okay to move?
Yeah.
Okay. I just saw lots of heads down writing. Kind of the last thing that I want to talk about here in section 1 is kind of rounding. I know, like rounding. We call this approximation and error is the fancy term, but really what we're talking about is rounding. And rounding is just the process of like estimating the value for a large or long number, right? So the way that we're going to do our rounding is the standard rounding that you've always done. You look at the digit to the right of the number you're going to round. If that digit is 5 or more, you round up. If it's less than 5, you round down. That's okay. So in this class, the standard direction is going to be, you should write your answer as an exact answer or rounded to 3 significant figures. Unless otherwise stated, but like if there's no direction in terms of like how should I write my answer, that is the standard expectation for all IB, is that you give an exact answer or an answer that's rounded to 3 significant figures. You guys hopefully all remember at having heard significant figures from your science classes. What's the purpose of a significant figure? Why do we use these specifically in science? And why don't I use these in math classes in general?
Your measurement can only be as accurate as your least accurate measuring device.
Yeah, that's a wonderful explanation. Perfect. So The significant figures are describing to the reader the accuracy of the tool you use to make this measurement, right? Like if I take a graduated cylinder that can read to the milliliter, and I have I have 10 milliliters, and in my calculation I divide that by 3, I can't report my answer is like 0.3 repeating, because that implies I have some kind of tool that can measure to the, like the picoliter, or more accurate than that, like it's implying you use some kind of hypersensitive tool that like you did not use. You used a 1 milliliter tool, and then you divide that number by 3. Dividing by 3 cannot make that measurement more accurate than when you started. Right? That's the idea. So when you keep that in mind, the rules for significant figures become a little bit simpler. Right? So, rule number 1, what kind of digits are always significant?
In front of the decimal.
Non-zeros. Right? Any non-zero digit is always significant. Everybody agree? Zeros are the hinge, right? So there's 3 types of zeros. The easiest type of zero that's always significant is the one that's sandwiched between 2 other significant digits. Those are always significant. Then we need to worry about leading zeros and trailing zeros. Leading zeros are never significant. So 0.005, just 1 sig fig, just the 5, because the zeros are at the front of the number. Trailing zeros are significant after the decimal. So 50, 1 sig fig. 50.0, 3 sig figs. Because the 0 after the decimal point is significant, which means the 0 in between is sandwiched, so it has 3. So 50, 1 sig fig. 50.0, 3 sig figs. And that's, I think, is the simplest explanation you can possibly get. Yes, sir.
Wait, is this like the stuff, like the Atlantic and Pacific, like the absent and present, like with the decimal points?
I've never heard that way of teaching it, but maybe.
So if you have like a number like 22, like point, like 325, so you already have like 5 sig figs there. Are you still just rounding to two decimal places?
You round into 3 sig figs.
3 sig figs.
So 23.3.
Yeah.
Okay.
You don't think that.
And maybe I did, and I just like tricked you for that.
I mean, the first thing that would be
So again, these are the sig fig rules. The nice part is, if we're talking about 3 sig figs as our kind of standard, almost always it just be 3 digits. Which is just like, okay, I just 3 digits is where I'm rounding to, and that's usually fairly easy, right? Like, and the nice part is, if the answer is a terminating decimal, do you have to do any rounding at all? No, because that's an exact answer. If the answer is a fraction, do you have to turn it into decimal and round it to sig figs? No, you just leave it as a fraction. If your answer is 5 root 2, do I have to turn it into a decimal and round it? No, that's an exact answer. I can just leave it that way. So exact is always fine. The only time you have to worry about the sig figs is if you're choosing to round. So if you have like a number that like fills up the whole line on your calculator, it's like, well, that's already rounded, because I'm almost going to bet that there's digits that keep on going on my calculator that I just can't see displayed. That's the situation where I have to think about it. Does that feel okay? So again, not every problem, only if you have to round, or if you're choosing to round. Some students will do, even if they have, 7/9 or something, they're going to round it to 0.778. Okay, that's fine. Still correct. Blah blah blah. These are all the rules that we talked about, right? Oh, also worth noting, when you're doing a calculation, the only time you should be rounding is at the final answer. Any step, prior step in that calculation, you're carrying all the decimals through. We'll talk about using your calculator in a way that makes that easier for us, which is probably something we'll need to practice a little bit, because there's always a temptation to like write down these intermediate steps rather than recalling the full decimal from our calculator. But our calculator is more than capable of doing that. We just have to know how to ask. All right. Bounds. So if I say that I have an answer that I've rounded to the nearest ones, my answer is 10. That 10 could have been really as big as 10.5 and as small as 9.5, right? You know, if it was a little less than 10.5, I rounded down to 10. If it was 9.5 or bigger, I rounded up to 10. So there's like some kind of bounds about what that number could actually be. So in our example here, we have the number 5 that was rounded to the ones place. That means it could have been, that number could have been less than or equal to 4.5, right? Because the digit to the left, no, to the right of the ones place could have been 5 or bigger, but it had to be strictly less than 5.5, right? If it was, you know, 4.4. 999999999, all of those gonna round. I'm sorry, 5.49999 would all round still down to 5, right? So again, the thing to remember here is that the less than or equal to is always on the lower bound, and the strict inequality is always on the upper. And again, that should make sense just based on your rounding rules, right? If this could equal 5.5, I'd round that up to 6. So it can't. And that's just my note about the inequalities. What if I said, okay, my answer is 5, but this time I rounded to the 10th place? Well, the digit I would have needed to consider would have been at the hundredths place. So I would be looking at, you know, 495 and 505, right? So depending on where we did the rounding is how we build the bounds out, right? If I round at the ones place, my bounds are going to happen at the tenths. If I'm rounding at the tenths place, my bounds happen at the hundredths place. You guys get the idea there, right? Again, this might be new as an idea, but like simple, not complicated, right? Like unfamiliar, but should be relatively easy. Yeah, we're good. We're just talking about rounding. It's like, Mr. Kulik, we're really talking about rounding? We are. Another thing, again, should be relatively familiar to you, the percent error calculation. How many of us seen this in our science class? Everybody raise your hand, I'm sure you all have. So it says the error is the approximate value minus the exact value divided by the exact value. We do the absolute value of that number and then multiply by 100 to turn it into a percentage. The thing to remember is that A is approximate and E is exact. So if we ignored the absolute value, we can get negative answers and we get positive answers, right? What would a negative answer tell us? That our approximation was less than the exact, so that we made a underestimate, right? If I ignore the absolute value and I get a positive result, that tells me that I had a overestimate. This feels like a homework question at some point. Now, when we report our percent errors, we always report the absolute value. But if you ignore the absolute value, it can still tell you something about your measurement, right? Whether you had an underestimate or overestimate. Even if you don't know what the estimate was or the exact value. all you know is that percent error number without the absolute value done to it, can still tell you something. And that was it. We did it. So good job, guys. Perfect timing. I don't have any assignment for you to work on. We'll worry about stuff next week. It's the first week of school. Nobody needs homework this week. At least from me. Maybe your other classes you need homework. But I'm going to spare you.
Thank you.